questions. Like most of them are just like, oh, is it okay? Do I need to have like the lone pairs in this? Like things like I've got things like that as well, which I guess I could ask when you're going through quickly, like, or is it okay if I write salt there instead of solid? Stuff like that. But all of this, that one I didn't know specifically, but then it's as well as like one section of.
So that's in the mark scheme, isn't it? That color?
It is, but I didn't know how to find. Like I was looking through the resources that I had, and I couldn't find it there either.
All right.
So, but it's just like that I do know. I just haven't written it.
Okay, you do know it. Yeah. Okay, all right.
Solubility.
She knows pretty much all of it, really.
Well, not all. Like I do struggle more with the electrolysis and
electrochemistry.
Yeah. That so like with this is an that equation I couldn't get with the vanadium. That's okay. There I have 2 questions to the NMR one, which might be I haven't touched that since like ages, so I'm really rusty that. That's maybe.
Probably if we're jumping into a question, we should probably do the whole question, otherwise we'll be losing context and any sort of preceding things that are in there.
Yeah, and then like there, it's asking if that has to be on top, which I'm pretty sure it doesn't. Like I could write that there or anywhere as long as ratios are right, and that's fine. And then that's okay. And this part I went to go play the piano, but probably got sick because it was a bit.
Okay, is that the end? You got
that is no, this is the last part. So those I didn't really do that. Yeah.
Okay, but there's nothing particularly difficult about those. You just hadn't done.
I'm not sure because I didn't actually.
Okay.
So yeah, but it's probably if it was easy, I probably would have done it.
Yeah.
So that we might want to look at it. Okay. It's about buffers.
Yeah.
And pH.
Yep.
That's just a formula.
Okay, so which question do you want to start with, Grace?
I don't know.
Okay, let me just have a look. So,
when you were doing maths before, and I was playing piano, could you hear?
No, couldn't hear the piano at all.
Okay.
I'd love to be able to hear it, but we couldn't.
No, I just don't. I was asking because.
Were you playing Somebody's Love?
I was.
Okay, I did hear it, but it was. I don't think it came across on the microphone.
Cool. So that's pretty cool. So like you can play piano whenever.
Yeah, whenever.
Whenever.
How good is that?
okay, so we did. We're getting to question 4, which is the electrochemistry.
Okay.
Is it?
So the transition metals chemistry, which then
goes
into the electrochemistry, and then you had so you've got a bit missing there, haven't you?
Yeah.
Oh, you told me that you knew that.
Yeah, I've gone through that with Tom lots of times, but we can go through that. That's that's something they ask in all the class papers. They do.
Okay, and this one here we haven't got.
Yeah, I didn't get that.
Okay, and I might just talk to you a bit about the working out the cell potentials, because you mentioned yesterday you were sometimes getting the signs the wrong way around.
I wouldn't mind doing that question.
Okay. So that
4 and 5.
Yeah, 4 and 5. So if we do 4 and 5.
Maybe the last. Or maybe the last instead of, well, I haven't, maybe the last, because that was a bit, the last 2 pages.
Start on 4.
Yeah, let's do 4 and 5, and then we can sort of scan the rest of the paper and pick up things.
Yeah, good thinking. Okay.
Good. All right, can you just take those, Grace?
So here's your pens, sir.
Okay.
We've got 4. I can do up and down if you want to.
All right.
And then, so, okay.
Okay, and we got.
Have a look at the mark schemes just so you know what they're looking for.
So that's all my stuff.
need a bit more space so you can have the mark scheme open and the screen.
Yeah.
You don't need this, do you? Because you can see it there.
Yeah, that's right. Okay. Okay, that's good idea.
Right.
So the microphone's on, isn't it? I've got a
It is
flashing light
on.
there. Okay, good. All right, so coming in on question 4, and it's talking about transition elements, and we've got a definition there of the term transition element. That's something you can look up in Chem Guide or in textbook. A transition element is an element that has one or more ions that has incompletely filled d orbitals. And I'm sure you got that right, Grace, when you looked that up. Okay, then you come down to look at some complexes of cobalt. And if you just scroll down there, you've got 3 reactions with hydroxide, excess chloride, and excess ammonia. What I'm going to do, I'm just going to focus actually on the first one there when you add hydroxide, because there's a lot of subtleties that are going on there, which I'm sure you've got the right answer, which I can see that you have, but there's some little sort of things in there that we should just check with you, okay? So I need some space on the right-hand side here, okay, so, and pen.
That's it.
Okay,
Right.
all right. So we're going to just write here the cobalt complex. So you've got that as what shape would you have that as, Grace?
Which one?
The aqua complex.
Octahedral.
Yes. So you'd always draw it, even though you normally say water is H2O, you'd draw it that way around, and you're going to draw the lone pair of electrons because you asked about that, and because it's octahedral, that's behind, and this is in front. So I'm drawing OH2 there, and then you've got these ones are called above the plane, aren't they? Here, they're called axial. You heard that word before?
Yep.
If it's above or below the plane, it's called axial. And if they're in the plane, they're equatorial. So, and over here, I'm writing the waters the other way around, just to show that the lone pairs are forming dative bonds. So that should be into the outside. So you got that. Okay, so that's our copper complex. And we're adding hydroxide ions. And the point that I want to go through here, I'll just pick up a rubber. Okay, that is, if I just expand that a bit. Oh. Okay, good. I'll go back to here. Okay, so that, okay. Now, when this...
Could be the button.
Yeah, that's right, I keep hitting that. So when the hydroxide ion is reacting with this, it looks like a ligand exchange, doesn't it? Because that's what you end up with. But actually, this is one of these acid-base reactions where the hydroxide is there and the complex is acting as an acid. It's going to donate its proton from there and add it onto here. So do you see what I mean? So it's not, it looks like ligand exchange, but actually it's acid-base behavior. And that's the kind of trick sometimes we had that thing that yesterday, you know, is it acid-base behavior or is it ligand exchange? It's actually acid-base behavior, even though if you write the equation out, it looks like ligand exchange.
And how can you tell that?
You just have to know that.
Okay.
Okay. Now, can you see there? I've done one proton combining with a hydroxide ion to form water. And so what would the formula of the complex be now?
CO, OH, and then H2O 5.
Yes. And the overall charge?
That would be till 1 plus?
Yes, why?
Because the OH, the cobalt is 2 plus, and the OH is negative, so.
Yes. Yeah,
At least
yeah,
one.
that's right. Okay, so now, so if you like, we've pulled off 1 proton, yes?
Yeah.
So now, would you say then that the complex that you form there is soluble or insoluble in water?
Solute?
Yes. Why?
Because you have an OH, and the hydrogen can, if you have H2O, it will react with that, and
No, you're talking about acid-base behavior there. Can you see this is a complex with a positive charge?
Yeah.
So you can think of it like an ionic compound.
so
Ionic compounds are soluble in water.
yeah.
So that's just a point. So now, so we've done the first step here, haven't we? So if we keep adding more hydroxide, what's going to happen next?
It'll keep displacing the H2O.
Okay, so if you like, we're going to pull a proton, aren't we, off this second water ligand here. Happy with that?
Yeah.
So still acid-base behavior. And once that proton's been pulled off, the formula for the complex is, what's the formula for the complex?
COOH2
Yeah.
and H2O4.
Yes. Now, at that point, what's the charge on the complex?
There's no charge.
Okay, so is it soluble or insoluble?
Insoluble.
So it's a precipitate.
Yeah.
So you now know why it's a precipitate. Do you see what I mean?
Yeah.
So that's just, you've done a little bit of a deeper dive here. It wasn't part of the question, but those kinds of questions, is it ligand exchange or is it acid-base behavior, and why is a precipitate formed, are, sometimes come up as a question.
Yeah.
Now, some of these transition metal complexes, you add hydroxide, and they form a precipitate. And then they say, well, if you keep adding hydroxide, well, if you took this example, if you added another equivalent of hydroxide, what would be the next complex that you'd form?
OH3.
So it would be cobalt, OH3. Oh, yeah, I'm still struggling with this pen. And water, ligands. Yes. And the overall charge would be, all right, now would that be a precipitate or soluble?
That would be soluble.
Okay. So you sometimes read in the textbooks that you add hydroxide, it forms a precipitate.
Yeah.
Then you add more hydroxide and the precipitate dissolves. And the reason it's formed a precipitate is because you cancel out the charges.
Yeah.
And when you added more hydroxide, then you started to get a charged complex again and it dissolved. Okay, so that we're doing a bit of a deeper dive here, but that's what's going on. And in the Mark scheme, they say the formula of was cobalt. Didn't they give that as the formula in the Mark scheme?
Yes, they did.
And
they give you.
Yeah.
You can choose.
Yeah. Okay. All right. So, but what do you think? That's not really the formula, is it? Because you'd added 2 lots of hydroxide, you'd removed 2 protons, and you'd end up with 2 hydroxides and 4 waters. So a much, much better representation is the one that you wrote down, is to say, well, there's still 4 waters attached.
Why is it okay not to write the water?
I don't know. Yeah, because
there's chemistry.
I think I'll tell you what the reason is. I think that it's one of those things in textbooks. There's a kind of once something gets into textbooks, it gets repeated again and again and again in the new edition of the textbook or in the exam.
Yeah.
So it's, it's a subtle point that it's much better to have that as the formula for the hydroxide. But because there's so much history in the way the textbooks are written, and many textbooks wouldn't have that, that they allow it, even though it's not as correct as the complex that you wrote down. And that's the kind of thing you'd have to talk about if they said, well, you add hydroxide, it forms a precipitate, and if you add more hydroxide, the precipitate dissolves. Talk me through this. You'd be going through that stepwise neutralization of each proton being taken off one at a time. And as you take one proton off, then it's still a complex with a charge, it's dissolved. You take another proton off, you've got a complex with no charge, so it forms a precipitate. Then when you add more hydroxide, then you've got a charged complex again, and the complex dissolves. So a bit of a deeper dive there. And then for the other two, those are genuine ligand exchange reactions. Okay, so when you added chloride ions, what was the formula of your complex that you had in here? This one.
And then CL4.
Now, why did you do CO4?
Because it completely, I don't know, it just is CL4.
Did you have a charge on that?
I have, 2 months.
Okay, yeah, we've got a charge, right. So you might have a question sometimes. Well, you started off with, you called it 6 coordinate complex, and now you've got a 4 coordinate complex. Why is that? That's kind of, it's not in this exam, but that's the kind of question that comes up.
Because, is it to do, no.
What were you going to say?
Is it to do with the, because of the data, the oxygen, which, no, I'm not sure.
Okay, all right. So where they go with this kind of question is to say something like, well, water compared to chloride is small. So it's much easier to fit 6 waters around a central cobalt atom, but you couldn't fit 6 chlorides because they're much larger. So that's why you end up with a 4 coordinate complex rather than a 6 coordinate complex. So I'm not tackling the questions in the paper, but I'm trying to give you the kind of questions that sometimes turn up. And then when you came to ammonia, your formula for the complex was?
NH3, 6.
Yeah, and why would you say you've got 6 ammonias?
Well, because ammonia is small enough to fit around 6 times.
Exactly, because ammonia is pretty similar size of molecule to water. So that's why you get 6 of them fitting around, because ammonia molecules and water molecules are about the same size. All right, good. All right, so scroll down then. Okay, for colors, this is one of the things where you just have to know them. There's no kind of way of working it out. And that's the kind of thing that I find most difficult, because you've just got to learn some colors here. And actually, personally, I off the top of my head, I don't know the colors, except that the typical color for cobalt complexes is pink. You start off with that. And these are colors that you're just going to have to learn. And I know you found it difficult to look them up, didn't you, today?
Yeah, I couldn't find that last one, but it's in the master. Okay,
so probably that's going to be, the way that you guys work. You probably have to hunt around various websites. Do you have a textbook that you use? Or?
Mostly Chemco.
Oh, really? Okay. All right. I mean, that's fantastic.
Yeah, it is great.
But, these are, if you had the official course book, then all this stuff will be covered for you. And these are things, unfortunately, that you're just going to have to learn. Okay. Sometimes, again, not addressing a particular question here, but the kind of questions that turn up, I might say, well, okay, what have you got? You've got solution B is blue. Okay, why is it blue? It's this kind of question that might turn up. So.
Because I don't know. Oh, wait, it's to do with something about the size of the ligands, isn't it? That's attached in comparison to what it was before. So
Okay.
I'm not entirely sure.
Okay, sorry. So where they're going for that is, so where they're going from those kinds of questions, when they ask you why is it that color, it's because its complementary color is absorbed and the blue is transmitted.
So like with the, okay, I got it. So
Okay,
like
so-
when you're just looking at the transition metals itself.
Yes,
Yeah.
Okay, so I think the complementary color to blue is yellow. Okay, so yellow light is being absorbed and blue is being transmitted. Okay, so the reason something looks a particular color is because part of the visible spectrum is being absorbed and the rest of the visible spectrum is being transmitted. So you just have to work on those absorbed and transmitted words to describe. And to say complementary colors is helpful as well. All right, good. Good. All right, so do you want to scroll up, Tom?
Mm-hmm.
Okay. This looks familiar. We had a defined standard electrode potential. We did that yesterday. Again, you could look that up. And it just means that you're looking at the potential of an electrode relative to the hydrogen electrode under standard conditions, which was 298 Kelvin and 1 atmosphere in SI units, that's 10 to the 5 pascals. Okay. Just while we're there then, what's all these standard electrode potentials are measured relative to the hydrogen electrode?
Yeah.
So what is the standard electrode potential of a hydrogen electrode?
0.
Yes. Okay, so it's hydrogen is just defined as the hydrogen electrode, standard hydrogen electrode being 0 volts, and everything is relative to that. Okay, got an electrochemical cell. We're going to measure the standard cell potential, and there's 2 half cells. One is a cobalt iron, cobalt metal half cell, and the other half cell is an iron 3, iron 2 half cell. And they're asking you what the electrode is here. And we touched on this actually last night, if you remember. In the first one, you've got a genuine interaction between the cobalt metal and the cobalt iron. So in this case, your electrode is the cobalt electrode.
Yeah.
But with the next one down, you're looking at the interaction between iron 3 plus in solution and in iron 2 plus in solution. So we don't want to put an iron electrode in because you've then introduced iron metal, iron 2 plus, iron 3 plus. It's not going to get too complicated. So you put in an inert electrode, and typically that's a platinum electrode. Okay. Now, you've got to write the overall equation for the cell reaction. So at this point, because we've got to figure bits and pieces out, I'd be looking up the electrode potentials for those 2 half cells in the data book. And because I'm just in the exam here, where's my pen? Okay, there you go. So the electrode is cobalt there. My writing is actually getting a bit kind of, looks like a 9-year-old's now. But a 3-year-old. And we had platinum for this, didn't we? I think in the mark scheme they give you some other ones as well, but platinum's a good, always a good choice. Okay. And then you've looked up in the data book the cell potentials for those, sorry, not the cell potentials, the electrode potentials for those. So what do you have for cobalt?
It's plus 0.28.
So we're putting the plus or the negative sign in there. Just to be absolutely clear. And for the iron 3 plus, iron 2 plus?
Plus 0.77.
0.77. I haven't checked those, is that correct?
Yes, correct.
Okay, good, all right. All right, so you were getting kind of, you had some questions about the you sometimes get the
Plus
negative or the
minus
positive signs. Okay, so I'll tell you what I think. I think that if you look through lots of textbooks, they all treat this differently. Probably Chem Guide has a way, different textbooks have a way. And so at the end of the day, everybody does it differently. So I could tell you how I do it, but that's no good. You've got to figure out how you do it. So, and the only way to do that is to do lots and lots of practice examples until you say, okay, I've got it. This is the way that I, Grace, do it, even though they have this way in the book, or you know, we did this in a tutorial or something like that. So the only way to really, really get it solid is lots and lots of practice. Having said that, I'll tell you what goes on in my head, and then if it's useful, you can use it. If it's not useful, then you've got to do lots of practice and figure out what works for you. The way I think about this is to remember that I'm working with electrodes, okay? And with electrodes, either electrons are traveling to the electrode or they're traveling away from it. That's the whole point of an electrode. Okay. Now, if an electrode has electrons traveling towards it, is it likely to be more positive or more negative?
More negative. Well, the electrode itself.
Okay, so the
would be positive, so it's attracting the electrons.
Yes, exactly. All right. So the more positive electrode will be attracting electrons. Okay. So which is the more positive electrode here?
The iron. The platinum. Or the point.
Okay, this one here. Okay.
Yeah.
So electrons are being attracted to that. It's the more positive. So I would say that's going to be, if I could write, electrons are going to be gained there. Do you?
Yeah.
That's reasonable. Now this one is more negative. So the more negative electrode would push electrons away. Kind of makes sense. So that one would be losing electrons. Yes?
Yeah.
Now you have to remember your mnemonic. You've got that in your head, haven't you? Oil.
Yeah.
I'll keep pressing this button here. So oil rig. I thought I was getting good at this. Okay. So oxidation is loss of electrons and reduction is gain. So we've already figured out which one's going to be gaining electrons and which one's going to be losing electrons. So which one's going to be reduction? Not looking there, looking at the, because I know you figured it out here. Yeah. I'm just talking you through my thinking. So we figured out that this one was losing electrons,
so that one,
and this one is gaining electrons. So what do you think for this one then?
That one's going to be oxidized. So
okay, that's an oxidation, yeah. And this one's going to be
reduction.
Yeah. So do you see? So what I try and do for this is that instead of trying to remember loads of stuff, just remember a few things like that mnemonic and something about electrodes. I know, I don't really have to think about it too hard to know that electrons will be attracted to the more positive electrode. I could, I don't need to remember that, I can figure that out. So it's all about what's the minimum amount of things that I can put in my head, and then I can work out the rest from first principles. So we pretty much worked that all out from first principles, but we just had to have that oil rig mnemonic in our head. Okay, so, and these, the data for these half cells in the data book is always written either, well, you tell me, is it written as a reduction in the data book or as an oxidation?
Reductions. Yes,
they're all written as reductions, okay? All right, so, you've got, now, what are the two half equations then? What's the reduction?
You're going to have Fe3 plus,
yes,
plus an electron.
Yeah.
Will give you Fe2 plus.
Okay. And that's a reduction. And the other half equation.
As a reduction or as an oxidation?
Right. Well, that's right. So the other half equation must be an oxidation, mustn't it? Because we've got the reduction. So the other half equation is?
Cobalt goes to cobalt 2 plus 2 electrons.
Yeah. Okay. And when you're combining two half equations,
you need to make sure that the electrons are the same.
Yeah, because you're going to cancel the electrons out later on. So you've got one half equation there, another half equation down here. What are you going to do to multiply them up before you combine them?
I'm going to multiply that bottom one by 2.
Okay, all right. So the stoichiometric coefficients in there is just 2 all the way through. And that means when we add it up, we're going to be able to cancel those 2 electrons. So the overall equation for the reaction is going to be cobalt plus, sorry, cobalt plus 2 iron 3 plus is going to cobalt 2 plus, writing's getting a bit better here, and 2, maybe 2 plus. And is that what they had in the mark scheme?
Yeah, yes.
Okay,
Yeah.
all right, good. Right, and we got that completely from figuring it out, and the only thing we had to remember was this mnemonic up here.
Yeah.
So that's, for me, that's the way I think about it. And I think it's okay because I figured out that electrons were traveling to or from an electrode, depending on whether it was more or less positive. So that's, you know, it's scientifically accurate, as well as being a helpful way of just remembering it. You see lots of examples where they kind of move things around and change the signs, and it's all a kind of a fix, and it gets the job done, and that may work for you. But at least in my method, it makes scientific sense. So I don't have to remember anything. I can just work it out from first principles. And I know if I went on to study chemistry further in the future, I don't know if you're going to do that, then I haven't laid traps for myself by having an incorrect kind of understanding. You know, at least it's sort of scientifically accurate.
Yeah.
All right. Okay, so those are our two half equations. When you look them up in the data book, they're written as a reduction, aren't they? So that one will be written as 0.77. But we've changed this one round. It was written in the data book as a reduction. We've expressed it as an oxidation. So because we've turned the equation around, then the electrode potential is no longer plus 0.28. It's going to be negative 0.28. You happy with that?
Yeah.
Just because I swapped it around from being a reduction
Yeah.
to an oxidation. And then in exactly the same way that I just added the two equations together, I'm just going to add these two together. So it's almost, you can almost do it in one step. You're adding two equations, and then you're adding these two values here, whatever they are.
Oh, okay. Wait a second. So it's probably negative 0.28, and I've already changed the sign because of yeah.
Okay, so yeah, just check that in the data book then, because I thought that was wrong.
Sorry,
when you
sorry.
said no.
Sorry. Yeah, so it's negative.
Use the rubber tool now. That's going to be a bit of a challenge. No, just good practice for me.
Sorry.
So that. Okay,
Sorry.
that's a negative there.
Yeah.
Okay, and because you've changed it from a reduction to an oxidation, then that sign changed. And so you've added the two equations together to give yourself the redox equation, and then you're just adding the values here together. So you're adding 0.28, which is positive, and 0.77, which is positive, and then you get the sum of those, which was 1.05. And just as good housekeeping, good habit, you have, even though it's implicit, you write it. I think it's good to do that. And you've got your unit, well, they give you the unit as well. So that you've got it right, but you probably had I don't know whether you had a slightly different method you might have done.
I wrote down the two equations and then I just reversed it, but I didn't. Yeah, I thought about that being the one that I didn't actually physically write down. That's why I didn't have the minus
Okay,
there.
all right.
But
I wonder why you reversed that one. What made that decision? Why did you reverse that one?
Because I realized when I looked at I did look at the
data book,
and that was more negative.
Oh, okay.
So I knew that it would be going that way.
You see, you've got something that works for you, and it gave you the right answer. So if that works for you, great. And the one that I did works for me, and I like it because it's I think about electrodes and electrons moving towards them, and it's scientifically accurate. But if you've got something that works for you, then that's much better than trying to use what I said. And particularly with these, it's a question of finding out what works for you. And the only way you can do that is to do lots of examples, like go to ChemGuide and pick up something. There'll probably be some examples on there to do, and just work through a bunch. And then if you mentioned something to me just now about something being more negative and more positive, and then helping move things around, just do that 10 times, and you really get set on it, and then your method is good to go. Or if you liked what I said, you could ditch your method and use this. But it's got to make sense for you, and what makes sense for me might be different to what makes sense for you. Okay, good. Do you want to move on?
Yes, what would you like to do next?
So we're keeping going. Now, this work on the Nernst equation, I think you just had to plug in some numbers, didn't you? It was all pretty simple stuff. And then you ended up with a difference in the electrode potential, and then you can work out that was actually going to give you an overall more positive for the cell potential. I think that's just arithmetic. And then you told me you got stuck on this point here with iron 3 oxidizing vanadium. All right, so let's just go through that. Okay, so it's giving you a pretty heavy hint here. It says use of the data booklet could be quite helpful. So I think that's a pretty heavy hint that you meant to use the data booklet here. So iron 3 ions can oxidize vanadium metal. So if iron 3 ions are acting as an oxidizing agent, the oxidizing agent will be reduced. Happy with that?
Yeah.
So iron 3 is going to be reduced. It's going to be reduced from iron 3 to Fe2 plus. So for one of the half equations, we already know that we've got that, haven't we? Okay. And you told me that was a reduction. Yes? And it tells us that the other reactant, because this is going to oxidize vanadium metal, is going to be vanadium. And we don't know what that's going to go to. And because this question is all about redox, when you combine to form a redox equation, you're combining a reduction and an oxidation, redox. So this must be an oxidation. Okay? So we've got to look up something in the data book that has vanadium metal, but because it's an oxidation, then when you're looking at reductions there. So
on the right hand side.
yes. Okay. So you've got to look through there and find a reduction that ends up with vanadium metal on the right hand side. What did you get?
These are all vanadium.
Now, which one gives you vanadium?
That's vanadium.
Where's the mark scheme?
It's here.
Where's that the other one?
That's the next page.
And you've got some more here as well, haven't you? Is vanadium on there?
No, not I can see.
Okay, so that's okay. So that's Is that the up-to-date data booklet?
Don't know, should be. Is there nothing on vanadium in there?
There is. Okay, so the only one they give you is vanadium going to vanadium 2 plus, isn't it?
Yeah.
So, I've lost. Okay. So that's the one they're giving you there.
Mm-hmm.
And oxidation is loss. So you've got that, haven't you?
Mm-hmm.
So to combine those two, you'd multiply that one by 2 and combine them, wouldn't you?
Yeah.
Which, and looking at the data booklet,
Mm-hmm.
that's what I would have come up with.
That's what I thought.
And then it gave you something different.
Yeah. So.
Okay. So I don't know why they've done that, unless the data booklet has been updated, because the reduction they're looking for is, so the oxidation that they're looking for is going to, what was it? It was VO, where was it?
Yeah.
This one, VO2 plus.
Yes, VO2 plus. Okay. So, and I'm expecting that to be in the data booklet somewhere.
Mm-hmm.
Okay, so just to work through, let's just take that one out, because that's the one that I would have taken if I hadn't seen the mark scheme, and I don't know why this one isn't in the data booklet. So when I have something like this, I write down the oxidation number of vanadium is, what's the oxidation number of vanadium there?
0.
Okay, and over here, it's,
4 plus.
well, you write oxidation numbers as +4. You happy with that?
Yeah.
Okay, that way around. Okay, so the oxidation number is going up. That's an oxidation, and we're expecting an oxidation. And an oxidation is a loss or a gain of electrons.
It's a loss.
So I'd write loss of electrons. So I'd expect electrons to be on this side of the equation. All right. Now, the equation that you had up there is balanced, isn't it?
Mm-hmm.
This one down here isn't. And so the way that you balance these redox half equations is with water and hydrogen ions. Okay?
Okay.
You with me?
Mm-hmm.
All right. So if you had to balance that with water and hydrogen ions, how would you balance that with water and hydrogen ions? Hydrogen ions.
I'd add hydrogen ion to the left side.
Okay. I would be balancing the oxygen first, because that's clearly unbalanced at the moment.
Oh,
Yeah?
so you'd need water.
Okay. So I'm now a bit happier, because I have one oxygen over here, I've got one oxygen over here. So the vanadium is balanced, oxygen is balanced, but I introduced 2 hydrogens, and I've got to balance those. So where I'm going to, because I can use hydrogen ions and water to balance, I'm going to have 2 hydrogen ions over here.
Mm-hmm.
All right. So your steps are write down the half equation, work out if it's an oxidation or reduction. If it's an oxidation, it's loss of electrons. Electrons go on this side. Then if you need to balance oxygen, use water. If you've got too many hydrogens, get some hydrogen ions in. And then last step is to say, well, look, this doesn't balance in terms of the charges. You've got 2 plus there, 2 plus there, you've got 4 plus overall that's not balanced. How would we balance that?
With hydrogen.
Sorry, I didn't read.
With do I need to add electrons?
We added electrons earlier on, we put electrons on here because it was loss of electrons, oxidation. And you can just write a stoichiometric coefficient in front of there.
So, yeah.
So the steps that you go through are write down the half equation, work out on which side the electrons go. They went on this side. If you've got an oxygen, balance it with water. If you've got too many hydrogens, balance it with hydrogen ions, and then make sure it's consistent for the number of charges. And we've added 4 electrons there, and we do a sanity check because the oxidation number has changed by 4 as well. So if that didn't match up, warning bells would be going off because you'd expect the oxidation number to change by the same number that you have as the number of electrons. Okay, good. So at this point, to combine the reduction and the oxidation, you're going to multiply that by 2, aren't you? So are you going to multiply that by 4?
Yeah.
Happy with that?
Yep.
So I expect 4 electrons, 4 Fe3 plus, 4 Fe2 plus, and then I'm going to combine those 2 half equations together, which gives me, coming off the end of the page here, water plus 4 Fe3 plus the vanadium metal. And what do you get on the right-hand side, Chris?
You have 4 Fe2 plus.
Yeah.
4. No, sorry. V. Vanadium oxide.
VO2 plus.
And then 2 protons.
Yeah. And you've cancelled out the electrons.
Yep.
And is that the equation that they had in the mark scheme?
That is the equation there.
Okay. So this is where I don't quite get it. It feels like that the data booklet is out of sync because we pulled that. You see the one that I crossed out? That was the only one that was available in the data booklet. But I'm assuming that in some other data booklet there must be that half equation.
Okay.
Well, you'd just have V going to VO2 plus, and then you have to do all this work on working out the number of electrons, which side they go.
Yeah, because normally they do give the electrons. They balance out for you.
Oh, okay, all right. So that's
nice. But yeah.
You can always do a sanity check because we looked at the oxidation number going up by 4, and then you're completing the half equation because they only give you the vanadium ions here.
Yeah.
Oh, they do give you the water and the hydrogen ions.
Yeah.
Oh, okay.
They're
So
nice sometimes.
So maybe I've overcooked that.
No,
But if you needed to go from just the vanadiums, then you balance it. You balance the oxygens with water, and you balance the hydrogens with hydrogen ions, and then you completed a completely consistent half equation, and you're ready to multiply up and
I
down
can
together.
do that with all.
Yeah, exactly.
Okay.
Yeah, that's right. Okay. So usually the clue that they give you is that the reaction is happening under acidic conditions because you're expecting hydrogen ion to be there.
Okay.
Okay, good.
Do you want to have a little break before you do the last 20 minutes? Or, yeah.
Yeah.
I think it'd be good.
Okay.
Give yourself like 3 or 4 minutes.
So,
a cup of tea or do you want some water?
just some water, I think. But
I'm going to go get some water.
yeah, good. All right, good. All right.
Do you want water?
No, I'm okay.
Do you want anything?
No, I'm alright actually. Thank you.
Cool. Okay, so what's happening now is I'm running this much more like a tutorial where we're picking up particular things that Grace has highlighted, and we're going off topic to look at the kind of issues that typically come up. So it's very different to what we did yesterday.
Yeah. I'm not quite sure that will work as well overall. It's a difficult one, isn't it? I mean, what?
I think it's very valuable for Grace.
Oh,
I think
brilliant for Grace.
We've been covering a lot of points that, she's done it. She's got everything right. So we're trying to cover things that are of value to her, but aren't 100% in the particular paper that you did.
Correct. And my way of doing it for physics, for subjects I know really well, is to say, okay, I'm sorry, I turned the mic on. That's fine. would be to say, okay, this is what they're driving at here, this is what they're testing, this is what's going on now. What we need to do is we need to make sure that there's lots of different ways, a bit like there's lots of different ways they can ask this. The principle is find a way of doing the balancing of equations, the redox reactions that make sense to you, that you can always fall back on. And I would prefer, so using your way of doing it, mine's traceable back to the science. I can always go, okay, which is more negative, all right, okay, and then the electrons, repulsion, I can always work that out. Now, the thing is, I guess, you've almost got to assume that people would watch 1 hour and a half of that paper and get that level of insight from you on all the most relevant bits. And by the time they've watched a few of these, they've got everything.
Yeah.
You can't possibly get everything because the questions don't relate to it. I suppose trying to work out.
Sorry, we only have mugs.
Thanks. Okay. Thanks very
Oh
much.
yeah,
Yeah.
we should get some glasses. I guess we need to get some glasses first then.
Everything's really high tech around here. You've got projectors, Apple Macs.
Oh, yeah.
It looks like a startup, and then you've got these things that look like they're from.
What is
True.
that?
Like
They're donated.
They were, actually.
Okay.
I don't think we'd have any cups. We haven't physically bought any cups.
A lot of stuff is donated.
That's nice.
We're just trying to say that it's quite valuable for you because these are the specific things that you're struggling with. Well, not struggling with, but it's the idea of wanting to be consistent. But I guess we need to work out how it's going to the balance between the coverage and then the specificity. And I think pace as well. I think it's a very different pace to a masterclass than to a one-to-one. Because I think this is kind of a pace of a one-to-one, isn't it?
Mm-hmm.
And a pace of a masterclass is the sort of thing that it's difficult to disconnect from that, knowing that.
Might be easier when other people are
I think so.
tuners.
I think so.
But it's always going to be about you, though, isn't it?
No, it won't always be about me. He's joking. But
So even we had a pastor come to talk to us the other day, and he said, "Well, I've got this course I want to put." Okay, what is it? It's grace is everything. So you can't escape.
Hilarious. No, but like if you said Joyce is going to come, so that's
Yeah,
what
Joyce will
that
be here
says.
the weekend.
She's coming the weekend.
She's going to be in school on Monday.
Great.
So she got her visa through yesterday, which is good.
So that
It's
is
another Joyce
Okay.
is
So
a
she'll be
girl who's doing A2 chemistry.
And it'll be-
Was she here last year? Or?
No,
No, she did her first year in an international school near Shanghai.
Okay.
She's coming to do A2. She's doing further maths. She's already done the maths. She's doing further maths, chemistry, and physics, and see how things go.
And you've done some Skypes or something together.
She's been watching these. Oh yeah, we've
Right.
done a few
Okay.
WeChat.
Oh, WeChat. Yeah. I know. Yep.
Which is very popular.
Yes.
And Joyce will be watching this. I
Okay.
imagine, tomorrow morning.
Okay. Did she see the one yesterday?
She had the link. I don't know if she's watched it yet. She's probably too busy being excited about her.
Hopefully she missed one.
They know that we're working on things.
Yeah.
And, it's going to be quite
And it
different.
might be different because I'm assuming she hasn't really done.
What I would like to reach, in the same way as the kind of the ZNotes have got a kind of a brand and a feel, I would like to, over the next few weeks, even months, if it takes that, to develop a style, which could be as simple as, going to night mode. This is what one of my guys was thinking. Well, if we just went to night mode, media looks different, right? And you could say, oh yes, that would be the kind of look.
Sepia? What about
Yeah.
the other one?
And that's consistent with ZNotes, which is quite black and branding.
We kind of want to be a little bit, but we're messing around. CPI, I don't think so. It's not
That's just weird.
Well, it doesn't even really show up. I mean, I thought that night mode wouldn't work well on the projector, but actually it doesn't look too bad.
It's okay.
That's all right. And then you'd,
It's a bit like though, like Khan Academy, like they have it
yeah,
in
they
black
do black,
and-
yeah.
Like
yeah.
yeah, but it's fun.
Obviously, you'd then change the pens,
Okay.
so you're
You
working.
need like a highlighter colour. or something.
Well, I think
Blackboard.
you go black.
What?
Yeah,
Why would you go black?
because I think then it is white.
Huh? Oh.
Because it's in that, because
Yeah.
that's actually black writing, but it's
Yeah,
showing white.
yeah,
So I
yeah.
think you go, you choose a colour that's black.
Okay, so we can look up complementary colours here.
Oh yeah.
Yeah, exactly. Yeah, I don't think I have to agonise over it.
Mhm.
But
But
from
I
that-
like the stuff like, sorry,
Go on.
Sorry.
Go.
I get what you're saying. So, because things like, for example, where was it? Before, how we were doing the acid-base reaction and you're talking,
The
like I had
complex,
that
yeah.
right, but you going through that was valuable for me
Of
and I
course.
think for everybody else. But, and then maybe skip
And
to the next kind of part where you'd have more of an insight. That might.
And what we could do is use the fact that people will have worked through the questions together and you and Joyce will have done some on your own and some together. Okay, well, to kind of almost have these are the 5 things that we think we'd want you to cover.
Okay.
And then send it to because the tutor will have obviously seen the paper and see the mark scheme. But if you say by the lunchtime, and so they go, right, these 5 things. So you kind of, that might, I don't know.
All right, so if Slack channel is, if that's active,
Yeah.
then the students might be piling on there a couple of days at a time, saying, or the tutor would pick up the particular issues to get covered in the masterclass.
Yeah, it could be. I mean, as I said, we'll work out the best way to do it as we go along. We're already so far ahead of where we were this time last year in terms of structure and systems. So, yeah, I mean, yeah, totally. In terms of our systematization.
Yeah.
In some ways, last year was brilliant and it's really exciting. We did lots of fun things and we want to keep the fun things, but be much more systematic right from the beginning.
Okay.
That's the plan.
All right.
Okay, crack on. Do
All
one
right.
more then.
So we do one more. We've got 2 minutes. All right. So this was the other one, Grace, that you flagged up, and all these sort of analytical techniques that it's absolutely normal that people find these the hardest. Actually, that's just so okay, and I'm
Oh, that was all. Okay.
There's some things where they just force you to remember stuff, and this thing about the m plus n plus 1 peaks and the relative numbers of carbon atoms in them, there's no shortcut here. You're just meant to know a formula that you. I mean, actually, is it in the?
It's not given. You have to remember it.
There's
Oh,
some
really?
stuff.
Okay.
There's some stuff in
But
the data book.
That isn't given.
Okay, all right.
The one divide that complicated.
Yeah, and really,
It's okay.
It's easy maths.
It's fine.
I don't know why they get you to remember this kind of stuff, but anyway. But just so I mean, maybe you just plug numbers into the formula, but what's the sort of basis of the understanding of that formula? Why have you got an m and why have you got an m plus 1 peak, and how's the formula constructed?
Okay. Are you asking?
Yeah.
Oh. It's something about the n plus 1 peak. Isn't that the carbon 13? The isotope.
Yes.
The isotope carbon 13, and it's always around. Is it 1% or
Yes.
1%?
Yes, that's right.
Of all carbons are
Yeah.
carbon 13. So if you know how many carbon 13s there are
Yes.
in that peak, right to the far peak,
Yes,
Right.
n plus 1.
then you can work out the ratio between them and then work out how many carbons there are in the whole compound.
That's it. Yeah. And this formula works for small numbers of carbons,
It works with large numbers of carbons, doesn't it?
small numbers,
Why doesn't it work for large?
because there's some approximations in the maths. And so the approximations hold for small numbers of carbons, which you only end up with 3 carbons here. But the approximations go sort of a bit off as you get to larger numbers of carbons.
Okay.
But you're right, that the natural abundance of carbon 12 and carbon 13 is about 99% carbon 12 and 1% carbon 13.
But statistically, shouldn't it get better if the numbers get bigger?
Not if it's a mathematical approximation that ignores things. I think what it ignores the other carbons, like the 14 carbons as well.
Okay. That's
Maybe
really,
not
but
sure.
that didn't, okay, I can
But
accept that.
you've got this formula and you're
Yeah.
plugging numbers into it.
Yeah.
And so you're ending up, aren't you, with, you're ending up with 3 carbon atoms
Yes.
here. Okay, and they told you earlier on that the M peak is 90. So we know that the relative molecular mass is going to be 90.
Whoa.
Yeah. Yes. I'm pressing the button again there. So you know you've got to come up with a formula which is going to be C. I'm fighting painting up.
If you go down, there's a C for you. If you scroll.
Okay.
Scroll
Also,
there's a,
Okay. All right. So we know that I was getting good at this. We had that break, and I've lost. Okay. So but that's 3. We know that, don't we? And we've got to get a molar mass of 90. So you've got carbon has relative atomic mass of about 12. Hydrogen relative atomic mass of 1, and oxygen relative atomic mass of 16, and we've got to add all this up, haven't we, to 90. So 3 12s, 36.
She knows that.
Yep.
yeah, it's okay.
Okay. And if we had 4 oxygens, we'd end up with 64, wouldn't we? There, which would start to push us over the 90 here. So let's step 1 back and have 3 oxygens, 3 16s.
That's 48.
48. 36 and 48.
84.
Yes. And that brings us below the 90 threshold, and we just say we'll make up the remaining. So our best guess at this point is C3H6O3. Okay, so you work that out. Okay, so scroll down. So the infrared spectrum is pretty easy stuff. You just look up things. Just one question here then. So why do molecules absorb, or what happens when a molecule absorbs infrared radiation? You're getting absorptions here, aren't you? So the molecule's absorbing the radiation, and it's absorbing radiation at specific wavelengths. So do you know what's going on? We're going a bit off topic here, just to...
No, but I'm guessing if it's... So it absorbs... No, I'm not sure.
Okay, so when you have chemical bonds, they can bend and stretch, and it's that bending and stretching of bonds that is absorbing the infrared radiation.
Okay.
So sometimes they might ask you, well, why is the infrared radiation being absorbed? Okay, it's not in here, but okay. So this is just actually the infrared spectra is pretty easy to look up, because you just looked up, didn't you? And what did you fill in for these things?
For the first 2.
Okay, so you got okay, so you got that, and the last one. Oops, last one.
It's a C double bonder.
Okay. Okay. So the possible functional groups then are you've got alcohol groups, and then you've got, what do you call this group?
Carboxylic acid.
Carboxylic acid. Yeah. All right. Now, will you just scroll down, Tom?
Sure. Scroll up on
Down.
Down. Yeah.
It was down.
Yeah. Okay, so we're getting into the one thing that really, like, all the students have difficulty with, which is the spin splitting in these proton NMR spectra. So again, because the way you use this is very, very personal. You've got to go backwards and forwards. There's no kind of method, really. It's just what you work out for yourself. And for me, before I dive into trying to analyze the spectra, I go back up and just try and figure out, well, what have I got so far? Because otherwise I'm trying to hold too much information in my head at once. So we've got molecular formula, and we've got these functional groups. At this point, I would be trying to sketch out some possible candidates, because otherwise I'm trying to hold too much information in my head. Is that what you did?
I did.
Okay, all right. So what candidates did you get?
You have, well, you kind of have 2 choices. You have the carboxylic acid on one end.
Yeah, that's obviously a terminal.
Yeah.
So it's going to be at one end of the molecule, isn't it? So you've got that, yeah.
And then you can either have the alcohol on the carbon next to it, or the carbon on the carbon.
Okay, so our candidates are either that, or you've got that, have you? I thought I was getting good.
Not bad.
So if this was me in the exam, I'd be sketching that down
Yeah.
more neatly,
Yeah.
so that I've got something concrete to hang on to when I dip into this more complex proton NMR spectra. Okay.
So do you want to go to
Yeah, let's scroll down to the, there's the proton NMR spectrum, and we scroll down below that, and they're giving us the chemical shifts, aren't they?
Mm-hmm.
And what did you get for type of proton and relative peak area?
CH3 group for the first.
Okay, so and actually it could be CH2 or it could be CH. It's that kind of proton environment. That's right. And the next one?
OCH2.
Okay, so that means there's hydrogen bound to a carbon atom, bound to an oxygen atom. Okay, and the next one?
ROH.
That's the alcohol group, is it?
Yeah.
And you're looking these up in the data booklet, aren't you?
Yeah.
Yep.
And then the carboxylic acid.
Okay. And then quite often they give you what's called an integration trace, which shows you the relative area under the peaks.
Mm-hmm.
But in this case, they didn't give you that. Mm-hmm. You had to kind of eyeball that a bit, didn't you?
Yeah.
Really. So you had, actually, if you look at those two, probably the relative area under this peak, or this, what do you call that, 4 peaks together?
Quadruplet?
Quartet.
Quartet.
Yeah,
sorry.
that's right. Yeah, that's it. And this is a
doublet.
Yeah. Okay. All right. And if you had an integration trace, you'd say, well, that if you integrated all those together, then they're about the same size. And this is clearly a different order of magnitude over here, isn't it?
Mm-hmm.
So just eyeballing that, I'd say, well, that's the same as that.
Mm-hmm.
And if I integrated all those together, it's about the same. And this looks to be more than double, but less than 4 times. Mm-hmm. We'll call that 3, which is what you got.
Sorry.
Yeah. Okay. All right. Good. So you've got your relative areas, which was it 3, 1, 1. Okay. They're being quite gentle on you here because instead of just saying, tell me the structural formula, they're kind of guiding you through. Mm-hmm. And then you've got to describe the splitting pattern at the first chemical shift. And you told me that was a doublet. Okay. So if you've got carbons and you've got a hydrogen there, and I call that carbon 1 and carbon 2, and that hydrogen is coming up as a doublet, what does it tell you about the number of protons over here?
That there's only 1 hydrogen.
Yes. Okay. So we know that from a doublet, there should be an adjacent carbon atom with only 1 hydrogen. Yes.
Yeah.
So it's. I think from the mark scheme, that's probably what they're asking here, isn't it? Is that what you wrote down?
Yes.
You've got a doublet, and there's only 1 hydrogen on an adjacent carbon atom, and then they do this last step here, where they're using this solvent here. Mm-hmm. What do you call that?
I don't know. Something like.
Yeah, actually, what do you call it?
Deuterium oxide.
Yeah, so I wasn't sure if it's like deuterated water or something. Okay, so deuterium oxide.
Yeah.
And when you add deuterium oxide, what can I scroll up to the pictures of the molecules again?
Sorry. Yeah.
No, I mean, that's the difficulty of doing this, is that on paper you can look up and down, but here you've got to scroll. Yeah. If you scroll up again. Yeah, those are our candidates. So when you add deuterium oxide, what actually happens to these candidate molecules?
The H's will be replaced by D's.
Yes, deuterium. Yeah. So that. What is deuterium, by the way?
It's an isotope of hydrogen.
Yeah. All right. So you get a deuterium can go there.
Mm-hmm.
Where else can the deuterium go?
On the OH. And
yeah. All right. And that has what effect does that have?
The peak doesn't show up.
Yeah, exactly. All right. So I think if you scroll down again, Sorry.
It's too big.
You
Done?
have,
No?
yep. Okay, so you can then say which of the absorptions are not present because they have been removed by adding deuterium. And then if you scroll up to our candidate structures again, we're looking, aren't we, for a carbon with one hydrogen on it. Okay.
I can put these down there if you want.
It's okay. I
Okay.
think we're just done.
Okay.
Really?
Oh, so you can drag things around, can you? Okay.
Yeah, I can just.
You just need to
Okay.
be
All right.
I'll leave them as well.
So
I'm
out of-
pasting them down here.
Okay, that's
Is it
very
down
cool.
here, you know?
Yeah.
So let's see if we can paste them. Look at that.
Okay, so out of your candidate structures, which one are you going to choose?
one on the left.
Yeah, because there's one hydrogen atom which is being, or one proton which is being presented as a doublet in the spectrum. And so that, for me, and I think for you as well, that becomes quite easy because we wrote down our candidate structures earlier on. But you know, if you didn't write down your candidate structures, you'd be trying to hold too much information in your head. So, you know, if you can put some candidates down, I think that's a very, very good habit, and you did that. Cool.
Done?
So we're done, aren't we?
Yeah.
But you know, if there are any other questions, Grace, that you had, we can, you know, we can turn the video off now. But just,
No, just do them on Slack.
Yeah.
of course. Okay. Yeah. All right.
I mean, I'll ask them. You can set him off now, but you know, the man has 8
No,
o'clock.
I don't have.
Don't
I
be
have a
selfish,
fiddly
Grace.
thing.
Say again.
Here.